thank you very much. Yes, I am blushing badly now. That's quite embarrassing. And of course, none of this would have been possible without a massive group of other people who I've had lots of conversations with and worked with and chewed over data with. So there's way too many people to list. I started listing everybody and it just filled up the screen and I would have missed people out. So you all know who you are and you're great. So thank you very much. Okay, so I'm just trying to think about what really to talk about for the next 10, 12 minutes. And obviously metamorphic rocks are beautiful. They occur in amazing field areas, so why not go study them? And of course, garnets are the best rock-forming mineral on the planet. But more importantly, they give us a window into previous plate interactions. So when plates shear past each other, when they get buried underneath each other, when they collide into each other, these metamorphic rocks basically record those processes as they're happening at the time, millions to billions of years ago. So that provides much more insight on long time scales than, for example, seismic data can provide today, which are very short time scales. And so we need to be able to link the two. So we've all seen pictures like this before of places where metamorphism happens in the Earth. Mountain belts form where plates collide. Subduction zones form metamorphic rocks as well. There's metamorphism happening at mid-ocean ridges, anywhere where hot rocks get intruded, hot magma gets intruded into colder rocks. But these changes are not instantaneous. They happen over millions of years, at least tens of thousands to millions of years. And if we're going to understand how the larger plate tectonics processes operate, so stuff that Alex Copley was talking about yesterday, we need to be able to interrogate when these changes happened, how quickly they happened, how long the changes lasted for. And in order to do that, we need to interrogate what metamorphic geochronometers actually record in these rocks. So what part of that long 10 million, 20 million year process are they actually recording? So traditionally we use different minerals to record different parts of the pressure temperature path, and on a fairly sort of blunt scale. So allanite and garnet were interpreted as recording timing of prograde metamorphism, and then thermochronometers such as rutile, titanite, micas, fission track, that was interpreted as recording parts of the cooling path. But we now know, of course, and as Owen has very clearly showed us in a couple of talks ago, that many chronometers are zoned. They do not record instantaneous growth, they grow over time. And also with thermochronometers, diffusive loss is generally imperfect. And there are lots of other processes other than heat, which can cause the daughter elements, isotopes, to be lost from these minerals. So the modern toolbox really uses high spatial resolution techniques to interrogate the zoning in these minerals and to use both the trace element and the isotopic compositions to link together for both the accessory phases that we're dating and, of course, the major phases that record the pressure temperature information. So we need these chemical reaction fingerprints to show which minerals are crystallizing when and to link the different bits of information that the different minerals record together. And modeling is really important here to help create this interpretive framework into which we can slot some of these ideas. But remember that all models are wrong and some of them are useful. And we'll go into that in a bit. So I thought I'd just pull together a couple of the things which are my favorites, I guess, of some of the metamorphic chronometer stuff that I've worked on. So when I was doing quite a lot of argon-argon work, and especially trying to understand what high pressure metamorphic rocks recorded in terms of their time, I developed this tool for understanding diffusion potential. So it's literally just pressure versus temperature with the metamorphic facies superimposed on top of that. This was particularly for white mica of different grain sizes held at those conditions for different periods of time. This particular graph is the 500,000 year one. Now, if you are retaining more than 80% of your argon in that time scale, you're never going to get a cooling age. You're not going to see it in the argon-argon data. So you need to hold on to these, you need to hold these minerals at higher pressures and temperatures for longer in order to actually get a cooling age. So these kind of graphs give you a quick snapshot of when a metamorphic rock might be able to give you an argon-argon cooling age. If that's the question you're asking of that rock, and this is the technique that you're trying to use. But we also found that lithology affects argon-argon ages because it affects the openness of the system, the ability for that argon to actually get lost and be released from the micas. So this was a study in the Cyclades in Greece, these low-angle normal faults, very low temperatures, less than 400 degrees C, so not temperatures, thermal diffusion is not really going to be a problem. But what was noticed was in the quartz-rich rocks, the micas were yielding much, much younger ages than the calcite-rich rocks. And the marbles themselves yielded these broader ranges of ages as well. And basically that's to do with which mineral is deforming at the time. In the quartz-rich rocks, the quartz is the strong mineral and the mica is the weak mineral. So as the rock's deforming, the mica is just getting shredded and recrystallizing all the time. And they're fairly permeable rocks, so the grain boundary is quite open. Any argon that's being released as the white mica is being torn apart can leave the system. Meanwhile, in the marbles, they're really impermeable, and it's the calcite that's the weak link. So the calcite is just kind of flowing and deforming around the micas, and the micas are retaining the age at which they originally crystallized, which is 20 million years before, compared to the quartz-rich rocks. So in total, some of my work on argon was basically looking at diffusion. I was looking at mineral chemistry, looking at deformation, recrystallization, the magic metamorphic fluids that we all talk about, and also the openness of the system. So there's quite a lot of tools in development to help distinguish between these different processes and help think about which rock, what the question is you're asking of the rock when you're dating it. That's basically the argon story, but there's quite a lot of work I've done on uranium lead as well. Monazite is particularly a great mineral, so Catherine will recognise this. This is from her work, where she showed that there are a lot of different generations of monazite in the same rock in different microstructural positions, and she can actually unpick different ages of them depending on where they sat in the rock. Now, these kind of data sets are quite rare. You don't often get places where you can really clearly see differences in ages, especially over, this is only 2 million years. So if you remember back to Owen's talk a couple of talks ago, he was looking at 1800 million year old rocks. You're never going to see a 2 million year difference in the samples. But what this means is that monazite was crystallizing and then dissolving and then recrystallizing and redissolving. And every time a new population was generated, it was then trapped by the major rock forming phases. So monazite's a bit of a tricky one. It records lots of great information, but it is also ephemeral. And if you don't trap it, it's gone. We also looked at partitioning of rare earth elements between garnet and monazite. So these were samples from Lucy Greenwood's thesis. There were monazites sitting inside garnet and monazites also sitting in the matrix and also in different structural positions within the garnets. So we could use the rare earth element concentrations in the garnets that varied from core to rim, and then also look at the rare earth compositions of the monazites that were co-hosted in them. And assuming that they grew at the same time, you could then sort of plot monazite over garnet rare earth element sort of lines, and you get these lines on the graph on the right here. Now, Brad Hacker pulled all these data together to show that there is a temperature variability between the garnet and the monazite, because what we found from the Himalayas in these non-melted rocks was quite different from what Daniele Robato had shown from higher temperature molten rocks in Australia. And so what's really neat about this is that we can start using garnet monazite rare earth element partitioning potentially as a thermometer as well as a chronometer, and as well as linking everything into the pressure, temperature, time history. So there's still lots of work to be done here, but it's promising and it's exciting. The final point I wanted to make really was that rocks in the same outcrop can record time differently, and Owen showed this as well. So here's an outcrop in Bhutan. This is where Lucy Greenwood was working, and she picked up 6 samples from the same outcrop, sort of unknowingly, just go along and pick six samples, and then was dating the monazites in these samples. And in these 2, labelled A and C, you get quite a range of monazite ages spanning a good few million years, which is quite a big chunk of Himalayan history. And in this particular sample, staurolite was present. But 2 other samples, labelled here G and H, had much smaller age ranges in the monocytes. So in one it was 24 to 20 million years, the other one was 22 to 18 million years. And so had, depending on, normally you go to an outcrop and you pick up one rock and you date it. And that particular rock might say, okay, metamorphism happened 22 million years ago. But unless you know that the rock right next door to it may be also recording 33 to 17 million year history, you're going to make massive geological errors in interpreting those ages. And so similarly to what Owen was showing, that different rocks will record time in different ways, and we don't really understand why yet. In these samples, the only difference between them really is some have got staurolite in and some don't. But staurolite's not particularly, useful for rare earth elements or for time, right? So why is this happening? We don't know yet. It's still work in progress, but we haven't done any of the mapping of the monocytes or any of the work that Owen's done on these, but there's still work to be done. But the important thing here is that geological uncertainty. People have drawn shear zones between outcrops in the Himalayas on less data than this, right? And this is just one outcrop. The rocks are 10 centimeters away from each other. So it's a bit of a whistle-stop tour, but basically in my travels through PTT space over the last 15 years or so, I've learnt, scarily in some respects, that petrology is always the key. Now I know we're all taught this at undergrad, look at the rocks, the answer will be in the rocks, and we go, yeah, but there's a whizzy machine that we can throw the rock at and it'll be, tell us exciting things. But actually the whizzy machines don't tell us very much unless we know how the minerals fit together in the rock. And time after time, when there's a complicated data set, it usually always comes back to the petrology in the end. The other important thing is the right analytical method. And that depends on what question you're trying to ask. If you want to know whether the rock is Precambrian or Paleogene, then it doesn't really matter. But if you really want to start unpicking things, processes that happen tens of thousands of years apart, then you've got to ask the right question and use the right tool. Many models, sort of pressure temperature modeling, diffusion modeling, is really helpful, but quite a lot of those do not match real rocks and they don't give you the full story. So they're all wrong, some are helpful. That's a really key point to remember. And there's lots that's still to be done on understanding when these accessory phases crystallize in the rock. So we know that monazite crystallizes and dissolves at the drop of a hat, but why and when and how? I think the partition coefficients between different elements in different major and accessory phases are going to be really important, because then again those can go into the databases and help us model pressure temperature information more successfully. And we need to have much more understanding on the geological uncertainty of our samples. Like the analytical uncertainty is tiny, the geological uncertainty is huge. And if we don't get a handle on the geological uncertainty, then we're just waving around in the air. So that's basically it. Thanks again for the award. I'm super flattered and very excited, and it did make the start of lockdown much easier because the news came right before lockdown. So that's, are there any questions?
Yay. Great, thank you so much, Claire. That was a wonderful summary of some cool stuff. And yay, monazites.
Yay!
Okay, do we have any questions? I'm very intrigued by your different monazites from the same outcrop. Yeah, I think there's some things we could look at definitely about other accessory phases and bulk compositions and fluids and.
Yeah, it doesn't seem to be related to apatite. It seemed to be sort of any staurolite related, but the uranium lead data are probably 10 years old now, and I think there's still more to do on those rocks before the story is tied up. It's high on my priority list of things to write up and investigate, but it's difficult to do from my spare room.
Okay, does anyone else want to ask a question, make a comment?
Or is everybody desperate for a beer and a cup of tea?
Allow you to speak. That was an absolutely fantastic way to finish our talk segment of MSG. So yeah, thanks for finishing on a high. And I think all the talks we've had in this session have been brilliant, and they've all kind of slightly linked together, which I quite like. And we have, yeah, lots of things we could learn from the different. Oh, maybe does Alex have a question? Do you want me to ask it? What is your view on slip rates through time in the Himalaya based on the variability you've shown in dating results?
That's a good question. Catherine, you can help answer this as well. So without doing more careful work across particularly mapped shear zones, that's a difficult question to answer. That particular sequence is not in a particular shear zone. All the rocks sort of across that part of the Himalayas are sheared, but it's all sort of just general, sort of nice, really. I think we just need to be more aware that any particular rock will only record a snapshot of the whole of Himalayan history. And we need to be much more aware of what those accessory phases that we're dating are recording. Like, when did they start crystallizing? When did the clock start ticking? Why did the clock start ticking? Was it to do with general metamorphism? Was it to do with deformation? So, yeah, there are lots of reports of different shear zones that separate different units with different pressure, temperature, time histories in the Himalayas, and quite often those are based on a broader sort of scale mapping, broader scale investigation. But yeah, the jury's still out in how the Himalayas formed on a micro scale.
Yeah, I think the great thing about the Himalayas is because it's relatively young, we can see all these complexities.
Yeah.
We can really understand how complicated.
The uncertainty on any individual age is under 100,000 years. So we can unpick things that happened on the scale of 1 million years, which you can't do when you're going back to the 1800 million year trans-Himalayan, not trans-Hudson or whatever origin.
Yeah, so John's just made a good point, saying that in the Lewisian, there are shear zones that have been drawn to separate terrains based on geochronology, but some is not supported by field relations. What's the best workflow?
Yeah, well,
to attempt a concise answer before tea.
I think that the stuff that Owen's doing, that kind of detailed interrogation of mapping of the geochronometers and figuring out what the geochronometers are telling us, because either the rocks have all experienced the same pressure temperature history but recording different parts of time, or they're experiencing different pressure temperature histories, and that's the difficulty that we need to unravel. But if you're drawing shear zones based on geochronological information and there's no information in the field, it's always going to be a bit sketchy, in my humble opinion.
I would agree.